Let's look at this problem. So this is a simple problem on actual vapor compression cycle. And here we have been provided with the properties at different states, right? And we have been asked to calculate the compressor power, refrigeration capacity, COP, and isentropic compressor efficiency. Now, this is a very simple problem, and most of the problems that we deal with in vapor compression systems are rather easy to work with, having solved much more complicated problems when we were dealing with Rankine cycles and its modifications in Chapter 8, or even the Brayton cycle and its modifications in Chapter 9. All right, so here we have been told that the table provides all the properties that we need for the vapor compression refrigeration cycle, and it is using R134A as the refrigerant. We'll talk about this more in a bit when we discuss refrigerants. The mass flow rate that is used is 0.08 kilogram per second. So as you can see, it's a pretty small mass flow rate that is used. Okay, so the first thing is to calculate the compressor power. Okay, so this is really straightforward. We have been provided both H1 and H2. So compressor power is simply m dot H2 minus H1, right? Mass flow rate times H2 minus H1. So we have the values already in there. It's just a matter of substituting the numbers in here. And when we do so, we get a value of 3.1 kilowatt. So it's a reasonable amount of power, okay? Not very high, not very low. Now let's calculate the refrigeration capacity. Now this, as I mentioned earlier, is one of the most important parameters when we are thinking about purchasing a refrigeration system or an air conditioning system for that matter. So this is a characteristic of the refrigerator or the air conditioner that you have, and basically defines its performance. So it's equivalent to Qn, right? The amount of heat that is absorbed in the evaporator. So it's equal to m dot times H1 minus H4. We already have these values here. And if the question had asked us to calculate the refrigeration capacity in kilowatt, we would just end here, okay? Just H1 minus H4 multiplied by the mass flow rate. But here we have been asked to provide the refrigeration capacity in tons. So what we need to do is we need to multiply by 60 seconds to convert the kilojoule per second to kilojoule per minute. And then we divide by the 211 kilojoule per minute to convert it into tons of refrigeration, okay? So this basically ensures that the final answer that we get is in tons. So it's basically 3.41 tons of refrigeration, which is a reasonable amount of cooling capacity. Now the COP. The COP, as we have discussed before, is simply the desired output, which is the cooling here, right? H1 minus H4, divided by the required input, which is the work input that we need to provide here. So it's H2 minus H1. So it's H1 minus H4, the refrigeration capacity, divided by H2 minus H1, the work input. Again, we have all the values, just a matter of substituting it in there, and we get this value of 3.86, which is reasonably good COP for a refrigeration system. As you notice, this value is greater than 1, right? The beta is always greater than 1. Okay, now let's talk about the last part, the isentropic compressor efficiency. Now we have been provided the value of 2 and 2s, so it's rather easy to determine that. From the definition of isentropic efficiency, we know that it's equal to the isentropic work input divided by the actual work input. So H2s minus H1 divided by H2 minus H1. This is again a matter of just plugging in the values, and we get an efficiency of 80%, which is again reasonable, but for other compressors, for example, the kind of compressors we were using in the Brayton cycle, we were achieving higher efficiencies. It simply has to do with the kind of fluid that you're trying to compress and a lot of other things, right? So this is not bad. This is reasonably good. But certainly if you can bring this down a little, bring this up a little bit further, right? Make it 85 or 90%. That will go a long way in reducing the work input that's required to achieve the same refrigeration effect, and basically increase the COP, which is what we always want, right? We want to spend the minimum amount of electricity to produce the required cooling effect. Okay, now let's talk about the Exergy analysis, right? This is one of the most important things that we would like to do as an engineer. We always want to optimize things. Now, we have discussed the Carnot cycle, and we came up with the definition for the maximum COP of a refrigeration cycle, right? Which is basically equal to the COP for a Carnot cycle operating between two temperatures limits Tc and Th. And this is how it is calculated. Now, we already discussed in the last class that although this is how you calculate the COP for a Carnot cycle, the COP for an actual cycle would also vary in the same manner like a Carnot cycle would vary if you play around with TC and TH. That is, if you bring TC and TH closer to each other, right? So if you increase TC or reduce TH, this is going to increase the COP of the Carnot cycle, but it is also going to increase the COP of the actual cycle. So this is a very simple tool if you want to think about it. It's a really simple tool that allows you to imagine what changes in TC and TH will change the COP of actual cycle as well. Of course, the changes that you get in a Carnot cycle and an actual cycle are different, but it happens in the same direction, right? So increase in TC will increase the beta for both Carnot and actual cycles, and reduction of TH will again increase beta for both Carnot and actual cycles. Now, as I mentioned before, the goal of Exergy analysis or second law analysis is basically to identify the regions or the components where the maximum exergy destruction is happening and try and reduce them in an economic manner, right? So economics is really important. We don't want to come up with a solution which is extremely costly, right? It really does not make sense and it's not practical. So the idea of doing exergy analysis for any component or any device, it's simply to identify first of all, right, where the destruction is happening, and then based on that we can make a decision on how we can reduce that destruction. Now, the way to calculate exergy destruction is through exergy balance, and you're all very well aware of this, having covered that in chapter 7 and even having studied for the midterm recently. So when we talk about refrigeration systems, we usually deal with a single inlet, single outlet control volume, which is at a steady state. So the exergy balance reduces to this more specific form. And for all the refrigeration cycles that we talk about, the changes in kinetic and potential energy are negligible. So the specific flow exergy change, which is EF1 minus EF2 for any given two states, is simply equal to the changes in enthalpy minus T0 times the changes in the entropy. All right, now let's go ahead and solve a problem based on this. Now here we need to calculate the exergy destruction in the compressor and the expansion valve of a refrigeration cycle. And what the process that we use here is very similar to what we have done earlier in chapter 7. The only thing new here is the fact that we are doing it for a different fluid, right? We have never used the R134A. We have used water, or we have dealt with air as a working fluid. So you just have to go to the appropriate tables, right? There's no other surprise in here. So for this specific question, we have been again provided with the properties, right, at all the states, 1, 2, S2, 3, 4, and also the entropies at 1, 2, 3, and 4. So let's start with calculating the exergy destruction for the compressor. Now, the general formula for exergy destruction is given in this manner. So the exergy destruction is equal to the exergy transfer associated with heat transfer minus the work output plus m dot times the change in the specific flow exergy, right? So EF1 minus EF2. So this is what we need for the exergy destruction rate for the compressor, right? Because it's going from the state 1 to state 2. Now in a compressor, we don't have any sort of heat loss happening, and actually there's no work output being produced. We actually have to provide work in. So as we know, work out is actually equal to minus W dot N. So when we write it in this form, when you write it in terms of the work input, this is how it's going to look like. So it's just work input plus the change in the exergy. Now, for this specific case, because there's no heat loss happening within the compressor, from energy balance, we can easily find out that W dot N, or the work input required, is equal to M dot H1 minus S2. So these two get cancelled here. What we are left with is simply the product of change in entropy times M dot. So if we substitute the values given in the question, right, and the table, for S2, S1, T0, and M dot, we get a value of 0.58 kilowatt for the exergy destruction of the compressor. So here we have not calculated the exergy destruction for an expansion valve, but in general, you should know that the largest exergy destruction occurs in the compressor when we talk about the vapor compression cycle. If it's happening in any other component, then that's something that you can figure out and reduce in an economic manner. So when you have calculated already this value, you already know that the exergy destruction for the expansion valve should be lower. If it comes out to be higher, you know there's a calculation mistake. Okay, so when you're doing this calculation, you should always have some idea about what to expect, right? I mean, of course, you can expect what this value would be, but you can expect which one would be larger. Okay, and if it's not, then that's a hint for you. All right, now let's look at the exergy destruction for the valve. Now for the expansion valve, again, this is the general form of the exergy balance equation when we're trying to calculate the exergy destruction. Well, in an expansion valve, there's no work output, there's no heat transfer. Okay, the specific thing about exergy, the specific thing about this expansion valve is the fact that it's an isenthalpic device. So the enthalpy remains same, right? So H3 is equal to H4. All right. So when we calculate the exergy destruction, the first part cancels out. Okay, we are just left with the change in the entropy, and when we plug in the values, it comes out to be 0.39. So this is as per our expectation, right? It should be lower than what we have here.